We are going to call it e-snack. Finally, I can finally use the merchandise nicely. Okay, e-snack. A huge thanks to Brian for sponsoring this video. Yeah! Doesn't that look absolutely fabulous? This right here, just it's for me the peak of chalkboard background. Just looks so good. If you also want to get one of those absolutely brilliant things, check out Sam Merch. You can get it over there to a pretty affordable price, if I may say so myself. It's not too expensive actually. Speaking of brilliant, it's our today's sponsor, and we're going to deal with a differential equation today, kind of interesting one. And if you want to know more about differential equations, I encourage you to check out Brilliant, because they do a really good job explaining differential equations to people, be it beginner or advanced people like me. Alright, so this differential equation right here has been sent to me over on my Cursed Math Meme site on Twitter, and actually I want to make an improvised session out of it, because yeah, why the hell not? But actually I was way too curious what the answer is going to be, so I actually solved it already. This right here is a second order nonlinear autonomous differential equation. Okay, they have the worst names ever, those differential equations, so like really long names all the time. And yeah, we are going to solve it today. The answer is kind of cool, special function related, so yeah, keep watching if you want to see the answer. So at first I would like to make a tiny little shift, because this right here is bugging me, and we can actually make use of a substitution to kind of make this thing right here a bit nicer. Okay, what we have here, I would like to simplify it at first. Also, if I were to substitute this, you don't have to listen to me say wow all the time for like 10 minutes straight. So at first I'm going to say let 1 plus wa be equal to, I don't know, let's take a variable eta. Okay, then we know if we were to differentiate both sides that our constant is going to vanish. This is where the magic is going to happen right here. Okay, so we know that wa prime is hence nothing but eta prime, and obviously wa double prime is hence nothing but eta double prime. And now we can plug those new names into here basically and see what we are going to get. We are going to get overall that eta double prime times eta is hence nothing but eta prime. And this thing right here is actually nice and separable, kinda. So not really separable, I wouldn't call it separable, but we can integrate it nicely with very nice antiderivatives, such that we are going to get one constant in already. So we are going to reduce it to a first order differential equation. It's going to be a linear one after that. This is good, right? I mean, this is pretty good. So at first I would like to divide both sides by eta. You're going to see why I'm going to do this. So we are going to divide both sides by eta under the condition that it's not equal to 0, and we are going to suppose that it's not equal to 0 because 0, so the 0 function is obviously a solution to this problem. If we have eta being equal to 0, then we just have 0 times 0 is equal to 0. This does hold. So after this case has been done, so 0 is one solution to this thing, we are going to assume that all the other solutions of eta are non-zero, so we can obviously divide by it. And now I would like to integrate both sides with respect to t here, because this right here is going to give us a nice antiderivative, and this thing right here is also going to turn out nicely, to be honest. So we are going to integrate both sides with respect to which variable? No, not eta, it's going to be t, because this right here is our variable that we originally differentiated with respect to. So let's integrate with respect to t on both sides. Now we are going to see what we are going to get here. I mean, if you take a look at eta double prime is nothing but eta prime, but this thing differentiated. If we were to integrate both sides, okay, then we are going to get the integral of the differential of a function here, and the integral of the differential is kind of inverse operations to one another. It's just a function in itself. So after integrating this, we are going to get eta prime out on the other side. Meaning overall, on this side we are going to get eta prime plus some arbitrary constant, suck more balls, I don't know. We don't care about the arbitrary constant, we are going to put it on the right hand side after we are done. So now, what about this right here? I'm going to go into a tiny bit of detail here, because I don't like to play physicist, and it's basically just substitution, so you can all make this rigorously in mathematics, and I have done a bunch of videos in my differential equations playlist already on this topic, so you can find the playlist on there at the top of the description. So now we are going to introduce substitution. Let eta be equal to some new variable. Okay, so let eta be equal to, I don't know, mu, for example. Okay, let's use some Greek letters today. And now we are going to implicitly differentiate both sides. So what is going to happen is what you are basically used to when doing substitution on integrals. So on this right-hand side, left-hand side, we are going to get the differential of eta with respect to t being equal to the differential of mu with respect to t. In normal case, since we differentiate implicitly, you're also going to get the differential of dt here, so just keep this in mind for a second. So now what do we have on this side? Well, obviously on the left hand side we are going to just get eta prime overall, being hence equal to d mu over dt. Since we are implicitly differentiating, we are going to get the differential, meaning after the substitution, so like I said, you can verify this result very mathematically indeed. After differentiating, we are going to get that d mu is hence nothing but eta prime times dt. And this is exactly what we are going to have here. And what we are going to end up with is just the integral of d mu over mu, and this right here is really tame. We know how to integrate something like this. This right here is going to turn out to be just the natural log of mu plus some arbitrary constant, I don't know, let's call it z for now, obviously. Okay, so we got this done. Now we are going to have a first order differential equation which is pretty much linear already. And now we can go ahead and just try to separate sides. Now we can use the separation of variables now basically. What we are going to do is we are going to divide both sides by this whole thing that we are going to have here, meaning we are going to get a function exclusively with respect to t on this side, it's a constant function, and everything with respect to eta. Don't forget, mu is nothing but eta due to the substitution. We're going to get everything with respect to eta on this side. Meaning overall, if we were to divide both sides by that, we're going to get eta prime over log of, okay, let us rewrite mu to being eta yet again. Log of eta plus some arbitrary constant c, being hence nothing but 1. And now once again we can integrate both sides, and obviously with respect to the variable t yet again. And the right hand side is extremely hard to do. I don't want to spoil it too much, okay? But the integral of dt is nothing but t plus some arbitrary constant kappa. Okay, so we are done with this side, but now here comes the harder part, this side. And this is kind of the exciting part of this video, if I may say so myself. We're going to introduce a formal substitution yet again. We are going to say let the denominator be equal to some other variable. I don't know yet, let's say which other variable is cool. Oily macaroni. So let log of eta plus c be equal to gamma. And now we would like to just do implicit differentiation yet again. So basically go through this process right here yet again. At first I would like to take base e on both sides because this really helps. So we are going to get e to the log of eta plus c is equal to e to the gamma. Meaning overall, after doing differentiation and some more elementary operations, I mean the differential of e to the gamma is just going to be e to the gamma, d gamma. This is just a regular substitution, implicit differentiation. Okay, what are we going to have here? I mean e to the log of eta is just going to be eta yet again. Okay, eta, but we are going to differentiate eta just like we did here. So meaning overall we are going to get eta prime and dt in some way, but also we are going to have up here e to the c, because e to the log of eta plus c is nothing but eta times e to the c, okay, just using exponentiation rules. So this right here is also e to the c. And now we just need to solve for what we had up here in the numerator originally on our integral. This right here is our numerator basically. So this right here is going to be something that's with respect to gamma. If we were to multiply both sides by e to the negative c, this is what we are going to get. Our numerator is going to be this chunk. Okay, meaning overall, if we were to plug everything in after the substitution, we are going to get t plus kappa on the one side. It's going to be equal to e to the negative c. It's not with respect to gamma, so we can bring it to the front of the integral using linearity, times the integral of, and now obviously this part is nothing but e to the gamma, and then d gamma. What are we going to get down here in the denominator? Well, we substituted everything to be just gamma. And here's where the kind of exciting part comes in, because this right here is not too elementary. I have made a whole series on this topic in my number theory playlist. Maybe it's also down there in the description. Just as a little reminder, we once introduced the general exponential integrals, the generalized exponential integral of order n in some way, and we kind of reduced it to being negative e1 of negative z. So this right here is negative, the exponential integral of the first order of negative z. And in normal case, this is known as the regular exponential integral with respect to z. And we define this to be the integral from negative infinity to negative z. Okay, we had upper and lower bounds incoming of e to the t over t integrate with respect to t. And I hope you can see the similarities here. I mean, what we have here, e to the t over t is basically e to the gamma over gamma, and it really doesn't matter what the upper and lower bounds are right here. So this right here is just the indefinite version. It really depends on your initial conditions that you have for this differential equation exercise here. So overall, what we have here is nothing but the exponential integral of gamma for now, okay? And after doing everything, so putting in initial values, etc., you're going to get a more explicit version out on the other side. So what we have here is the exponential integral of gamma. But we can actually go a step further because we know what gamma is. Gamma was exactly log of eta plus c. So this right here is nothing but the exponential integral of log of eta plus c. And we also know what eta is. Eta at first was 1 plus y. Okay, so this right here is log of 1 plus y plus c. Meaning overall, if we were to multiply both sides by e to the c, it's never equal to 0. We are going to get a final, very weird expression for our y, kind of, okay, which is that the exponential integral of log of y plus 1 plus some arbitrary constant c is hence nothing but t times e to the c plus, okay, e to the c times some constant. Both are constants, and if you multiply constants together, it's just another constant. We are going to call it e-snack. Finally, I can finally use the merchandise nicely. Okay, e-snack, for frick's sake. That's another constant, and it's basically it. So the thing is, in normal case, you would like to also solve for y at the end, but kind of hard because the exponential integral is not too nicely invertible everywhere. So it really depends on your initial conditions if you can actually find out an explicit formula for y. But it's good enough. I mean, it's some kind of solution, and maybe in some domain, the exponential integral is actually invertible, and you can solve for your y. Okay, so good luck with that. I hope you did enjoy this video. But before we end the video, okay, I would like to get back to what I said at the beginning, namely that our today's sponsor is Brilliant yet again. And if you are really interested in differential equations, be it more advanced differential equations or just the basics, then you should definitely check out Brilliant. Here's a short and spicy introduction to Brilliant. It's an online learning platform and app which offers you an interactive learning experience like no other on the internet. No matter if you want to scratch the surface of differential equations or want to go beyond the important fundamentals, Brilliant has you covered with over 60 interactive courses in all disciplines STEM, including calculus and analysis, of course. If you wish to get a deep and intuitive understanding of the mathematics behind differential equations, integration and differentials in general, then definitely make sure to check out their magnificent Road to Calculus, Analysis or Differential Equation courses. All of them will offer you a wide variety of topics being covered and will help you unravel the most important parts of the theory bit by bit. So if this feels like something for you, make sure to check out the link at the top of the description. With it, you're going to get free access to a big portion of Brilliant. So you can already try out some differential equations or, for example, linear algebra if you like. But even better, the first 200 people to actually use the link get 20% off an annual premium subscription, which is a really great deal considering how much content they already have over there. They have such a huge library of courses already. It's absolutely amazing. So check it out and support the channel this way. It's really worth it. I can recommend it. I love using Brilliant. You can see it on my live streams, for example. Other than that, thank you guys for watching. If you subscribe this video, please like, subscribe, and comment channel like. If you want to support the channel a bit more, go over to STEM Merch and check out our stuff. And up until the next video, I'm wishing you guys a flammable day. Don't forget to also go over to Flammable Maps too. So much stuff I want from your subscribers. Love you guys, appreciate you. Thank you for your continued support. Ciao.